Okay, so let's continue this and derive the expression for rotational effects in this tank where we are doing this special experiment. We had gone through this and showed that the radial balance in a non-rotating framework, which means if we are standing in the lab and looking at the tank, then it was V theta squared over R equals 1 over R partial P partial R, where V theta is the total azimuthal velocity in the non-rotating framework. So it is just relative to the tank v theta plus the omega r, rotational speed because of the tank's rotation, right? So tank is rotating at omega r and the fluid is rotating at small v theta. So if you're standing outside, what you will see will be the total v theta plus omega r. Okay, that's easy enough. So using our hydrostatic approximation at any z here, the pressure is going to be the water column above, so it's going to be rho g times h minus z, right? Z is from the bottom of the tank to that level, and h minus z is the water column above. Okay, the vertical velocities are relatively small compared to the inward flow, the rotational azimuthal angle flow. So that's our justification for using this relation. Obviously flow is going down and into the tank, so it's not strictly valid, but we are at slow enough speeds. So in the non-rotating framework, the radial balance now with this expression dp dr becomes g rho g dh dr. So v theta squared over r equals g dh dr. That's fairly straightforward. So again, v theta is the relative to the tank plus the tank speed. That's our expression. And in a non-rotating framework, the total can be expanded to get a, you know how to expand this one, v theta squared plus omega squared r squared plus 2 omega r v theta divided by r, and this is what you should get. I'm sure you know that, but I'm just trying to make sure that we are on the same page. So v theta squared over r plus 2 omega v theta plus omega squared r. We'll introduce a reference surface here to simplify the expression further. We'll come back to this a little bit later on, but the reference surface is provided by setting up a solid body rotation in a tank. So in this tank, the rotation is first set up where, after quieting down the entire system, a slow start is made and water is introduced at the edges, okay, with a speed omega r to go with the tank, and then at some point you open the plug and you get the flow out. But in this case you are going to get a solid body rotation. So if you're careful, you can make the entire fluid rotate with the tank without any relative motion with respect to the tank. So the whole liquid is rotating as a solid body. In that case you get this parabolic surface, which can be used as a reference surface, which is what we will do here. So measure the height of the free surface with reference to the parabolic surface, which is given by omega squared r squared over 2g. It comes about basically because you have rotation rate omega and then the radius of the tank and the balance needed to maintain this solid body rotation. Okay, so then eta can be written as h, again the back to our tank, minus omega squared r squared over 2g. So we are measuring the height of the water column for this pressure as the difference from that reference parabola we would have and the actual h that results when we pull out the plug. So this is the actual h that results, and the reference parabola is somewhere here that you would have before the draining started. So we can then take the derivative of this in the radial direction, gives us d eta dr equals dh dr minus omega squared r over g. What what does it get us? Basically, we get a simplification that looks like this. In the rotating framework, the radial balance will be given by v theta squared over r, the speed relative to the tank. That's what has to be balanced by the pressure gradient and the centrifugal force. Pressure gradient, yes. So you have g d eta dr minus 2 omega v theta. Okay, that's in the rotating framework, which is equivalent to what we had written in the non-rotating framework, where v theta is the total velocity of the tank plus the liquid with respect to the tank, is just g dh dr. Okay, so this is the term that's introduced because of the rotational effect. If you're in the non-rotating framework, standing outside and looking in, this will be the balance. The surface is tilting, and there's a pressure gradient in the radial direction, and there is a centrifugal force because of the total azimuthal velocity, and they are balanced. But if you go into the tank and look with a camera that's rotating with the tank so it can see things in the rotating framework, then you are balancing the motion of the fluid in the azimuthal direction, the centrifugal force because of that, and the pressure gradient, as well as a term that is introduced because of the rotation, which is essentially on the planet what we would call the Coriolis acceleration. That's the big derivation in this part, that if you're on a rotating framework, you have an apparent force that's going to create a additional term in the balance of forces. This leads to many interesting solutions that are very elegant and so on, and we will see that at all scales. So anytime you move at planetary scale, even a water in a cup of tea, coffee that I'm drinking will feel rotational effects, but they will be too small. In the tank we created by rotating the tank itself, and it is the rotational effect in the tank, and it is just like the Coriolis, so we are calling it Coriolis, even though Coriolis is typically the planetary effect, but any rotational effect you would feel can be referred to as Coriolis. And we'll see that this is not a real force in the sense it doesn't do any work. It doesn't accelerate the fluid, it just will change the direction, and we'll see how that differs from hemisphere to hemisphere and so on.